All right, so this is for today's notes, beginning chapter 9's electricity chapter. Let's go ahead and pull this up. Now, you have undoubtedly heard the term static electricity before. The thing that's funny about this, I guess I find it funny, is that static is usually used by most people as like a magic word. Like, what happened there? Static electricity. They don't really know what went on. They know it's probably something to do with that. The word static, at its heart, just means not moving. That's it. That's all it means. So it's electricity in which the charge is not really moving. Now, this is a little bit of a misnomer because it does actually move in static electricity, but usually when there's movement in static electricity, it goes somewhere and then pretty much immediately stops. Now, for those of you guys online, I'm going to tell you right now, a lot of today is going to be hard to track online due to the fact that I have a bunch of electricity examples here in person that you're going to hear me talk about. So I will try to do my best to describe it. Obviously, you have the textbook, and then obviously you'll see it when you get back in person. Yeah, and I'll try to suggest some things maybe to look up while we're doing our thing. Here we go. All right. So the basic rules for all of electricity. Where does charge come from? Well, let me ask you a different question. Where does mass come from for motion? Atoms. Correct. And you've got the exact same answer for this question as well. Now, if you'll remember at the very beginning when we talked about mass, I'm going to kind of fix a little bit of a definition, but not entirely. Excuse me. I told you that mass was what? I told you it was an incorrect definition. But what did I tell you mass was? Number of atoms. Yes, how many atoms are in an object. And I told you at the time it was an incorrect definition. And honestly, now you start to see that when you get into chemistry and the like, because obviously atoms can be different sizes. You look at that your periodic table over here, and you look at the relative amounts of mass. Hydrogen is 1, helium is 4, meaning helium, and there's some other decimals that we'll talk about potentially a little bit later. Okay. Helium being 4 means that helium is 4 times more massive than hydrogen. So I'm going to adjust my definition ever so slightly and still make it wrong. Okay, mass is not the number of atoms in an object. Mass is the number of protons and neutrons in an object, which is closer to the correct definition, albeit still somewhat wrong for a couple of reasons. All right, so that's not important. Charge, where does it come from? Charge comes from the atom. Specifically, you've done this a bunch in chemistry. We have electrons and protons and neutrons and all in the spots that you definitely know. Now, here's the thing that I need you to get out of this real quick, and it's this. We reviewed a couple days ago the fundamental forces, okay? And I asked you, what are some weird things about the atom? And one of the weird things about the atom is, of course, that all the positives are in the middle. Why is that weird? They should be repelling. And they are. So why don't they repel? Why don't they go all over the place? Neutrons. Specifically what force? No, it's not the force that we're talking about. It's in the nucleus, you're right. Strong force, correct. It's the strong force, but the specifics are not super important. Okay, the main thing to get out of that, I'm skipping ahead, aren't I? Yeah, actually, I'm skipping to point 3. My apologies. Okay, let's talk about this for a brief amount, and then I'll go back to that particular comment. Charge is conserved. It always goes somewhere. Meaning that, albeit I'm going to struggle sometimes to see where some of these things go, charge, yeah, I'm not gonna lose negatives. Negatives do not just appear, they do not go away. Conservation of charge is practically the exact same thing as conservation of mass. If I have an electron in one location, I don't expect it to go away. I expect it to stick around, and as such, it should have the exact same charge. All right, going back to what I was talking about a second ago, blah, 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 just remind you, okay, neutrons in the middle have the strong force. So, do we expect anything in the nucleus to move? Not really. Because what does it take to move anything in the nucleus? Let me ask this differently. If you need to move electrons, those are, you got the idea already. If you need to move electrons, those are chemical reactions. If you need to move anything in the nucleus, those are nuclear reactions, right? Yeah, so we don't expect on a normal day for protons and neutrons to move, which means when we start talking about the charge of an object, we're primarily going to be focusing on an object's negatives. Okay, so I want to go over that. Yeah, let's do this real quick. Actually, we'll come back to that in just a second. So, in other words, I'm going to make this way too simple. You have an object, okay? And in that object, there are negatives in the object, okay? And there are positives in the object. And so naturally, based on that, what would you expect? I am getting ahead of myself, aren't I? It's no big deal. It'll work. What do you expect the charge of this object to naturally be? What's that? Zero. You'd expect it to be neutral. But not because it is inherently neutral, like a neutron, but because simply most objects are neutral, meaning they have the same number of protons and electrons, aka same number of positives and negatives. So in other words, this desk that is standing in front of me right now, what charge do I expect it to be? I expect it to be zero. You might say, well, wait a minute, how do I expect it to be zero? Well, think of it like this. If it wasn't zero, pick a charge. Pick a charge it could be. Positive, great. Everything that's running into it all the time, what is regularly running into this desk? I'm going to say no, you're not regularly running into this desk currently. No human being is currently running into the desk that I am pointing to despite my proximity to it. What is running into it all the time? Air particles. Now, air carries with it positives and negatives. So if this was positive, what is it going to do to the negatives in the air? Attract it, pull them off. And eventually it's going to pull enough negatives off that it is now neutral. Or you might say, what if it was negative? Well, we'll get to that in a second, but essentially what do negatives do to other negatives? Repel. So you got a bunch of negatives on this to make it negative, and they're repelling each other, trying to get rid of themselves all the time. Let's go back over here and hit this up. All right, here we go. So what are the basic rules? We talked about this the other day. The basic rules of all electricity are positives repel positives, negative repel negatives, or the fancy way, the easy way to say that, not fancy, is to say that like charges repel and opposites attract. And let me be careful on this one. When this says neutrals do not affect an electric force, they are of course referring to neutrons. They are not referring to what I will call from this point forward macro objects. A macro object, there's three basic scales we usually have to concern ourselves with in physics. There's technically more, but there's like three main ones. And that is the macro scale, the micro scale, and the atomic scale. Okay? The macro scale is literally anything we see around. So if I say on the macro scale, this is what I was just talking about with this desk. I point to the desk, I go, what charge is it? You say neutral. Why is it neutral? Because it has the same number of positives and negatives. That can actually affect the electric force because it has positives and negatives in it. But neutrons certainly are not going to do anything. All right, these are the basic rules. These are the rules. Everything you hear me talk about today is based on these relatively simple rules. 1, all charge comes from the atom. 2, charge doesn't disappear, it always goes somewhere. 3, only negatives move. Positives don't really move because the strong force is holding them in place. And finally, like charges repel and opposites attract. Neutrals do nothing. Okay, I got ahead of myself. We already talked about this. What's the normal charge of macro objects and why? Boom. We said it's already neutral because it's the same number of protons and neutrons. All right, so what does it mean if an object is negative or positive? All right, well, let's go back to this picture I drew just a second ago. Okay, here I have a dumb picture of a random object. Obviously, it wouldn't be constructed like this because I didn't take care of exactly where. Oops, that's not the button I wanted. Here we are. Let's go over here. Okay. All right. So this object is the object on the left is neutral. The object on the right also neutral. So what could I do? Simple thing to make it negative. Careful with that. What rule that we already said that you're breaking? Can't move positives, right? Well, in general, we'll just say you can't move positives. So erasing a positive is taking a proton out of an atom. Please tell me if you're going to do that on a particular day. I'm not coming to work that day. Okay, as a matter of fact, I'm taking the rest of my family and driving as quickly as we can away from your general proximity as we possibly can. So not an option. What should we do then to make an object negative? Add negatives, correct. We need to add negatives from somewhere else. Now, I'm just going to do some basic math here. Here we have, of course, 4 positives, 8 negatives. Obviously, these numbers are a little bit smaller than the actual amount, but that makes this guy negative. Why? Negative, in general, means excess electrons. And we've already discussed this. Do objects inherently want to stay negative? Nope, because what do negatives do to other negatives? They repel. So they try to push away as much as they can. So we'll talk about methods to do this here in just a second. But let's move on. Firstly, let's move you. Okay, you go over here. Okay, and we still have one of these. Cool. All right, so how do I make an object positive then? Yeah, because a lot of people want to go to like, well, if we add electrons to make a negative, certainly to make it something positive, we need to add protons. See previous conversation on why that is a terrible, terrible, terrible idea. So let's go ahead and erase. Sorry, just literally told you not to do that. Wrong one I'm erasing. Just caused a nuclear disaster. Okay, erase the right one, get rid of those negatives, and now an object is positive, not because we have added protons, but because we have removed electrons. Actually, let's not go with remove. Let's, because I regularly use this other phrase. Let's go missing electron. No, this is very general. This is very nondescript. You go, great. You're drawing pictures of tiny little things. How can we do that on a macro school? Actually, I think I'm getting ahead of myself. Hold on a second. It's been a minute since I've done the slideshow. I apologize. I'm showing my struggle here. All right, a couple other things to hit ahead of time. A couple definitions that are ridiculously important. One, conductors. There's 2 definitions that you need to understand about a conductor. First one is the one that everybody knows, and that is a conductor lets electrons flow easily. Okay? Generally, what are you looking for if I say conductor? Metal. Now, ultimately, please understand that conductor is a little bit of a generic term. It applies to any material that lets electricity flow easily. Ultimately, what we do to find out that something is a conductor is experiment. You put electricity across it and see how well it goes. Okay? Most people, when I comment on conductors ahead of time, not knowing, think like, oh, everything has to be a conductor in electricity. No, absolutely not. Because the second thing is something that's bad about a conductor. I guess not necessarily bad, but also true. And this is just the same way to say the same definition. Okay, it's the exact same definition, but said in a different way. One, it does not hold on to electrons well. So if I want to hold a charge in a particular location, should I use a conductor? Probably not. Of course, insulator is the exact opposite. Does not let electrons flow easily and holds on to electrons incredibly well. What are some examples of insulators that you know of?
Plastic.
What's that, plastic? Cool, plastic is good bonus. I'll be straight with you. Honestly, it's most other things we would qualify as an insulator. Now, how good they are at being an insulator is a measurement that I don't think we're going to get into in this class. Um, it's actually mathematically measured. We'll talk about that potentially in physics too. But an insulator is almost everything else. Like the top of this desk is probably an insulator. Um, my clothes are probably an insulator. Okay. Do you know what the biggest insulator is on a human? Well, I'm going to say close to that because actually different tissues, depending on which one we're talking about, I'm going to say skin. Okay, the biggest thing that protects you ultimately from electricity and getting is your skin. What is the biggest insulator probably in this room? What's that? It seems very not. You're close, but not quite. No, not the room.
That insulation between the walls.
No. What in this room, what material in this room would be the hardest to get electricity to probably pass through? Two of them are probably out there, but one is definitely the right answer. Any guesses? Any other guesses? Second place, I would say, is probably like the cabinets or wood that is used, that it is in those particular desks. You can kind of see that a lot of the desk is made of particle board. But the biggest insulator in this room is air. Why? Well, is it going to be very easy to get electrons to jump through air? Why not? It's a very simple reason. If you zoom in on air and think carefully about air, you can very easily kind of picture why it is that air would be the best insulator, or why it would hold on the best or keep electricity from flowing through it. Yep, that's it. Simply because they're super spaced out, making that jump is a lot harder to do. Now, does that mean you cannot get electricity through an insulator? No, you just have to try harder. Which gives me to my first demo of the day that hopefully some of you have seen here before, because it is one of the favorite demos that people have. Okay. You will use it periodically throughout. It's known as the Wimhurst machine, but it is essentially a lightning creator, as it were. Okay? Now, I'll talk about the specifics of this a little bit later on so you can roughly get a gist of what it is that's going on. But in a nutshell, here it is. I'm going to spin the wheel back here, okay? That turns these guys up top. If I position this correctly, feels like this thing breaks all the time. Regularly having to put it back together. This will work for right now, though. Should those are positioned correct? Positioned correctly. Here we go. In a nutshell, what you just saw is electrons jumping through the air. It's jumping from one side over to the other side. Now, obviously, that is not easy to do. And because it is not easy to do, gotcha. All right. Does she have a loaner for you? Yeah. Okay. Sean? Because it's not easy to do is the reason why you see that light and you hear that sound. It requires an incredible amount of energy to jump through the air. As it uses that amount of energy, conservation of energy says that energy has to go somewhere. So we pull that in, we use that energy to pull it out of the air, and it comes out in three different forms. This is just like a ball, essentially, going down. If I drop a ball, if I drop a ball, how does its energy come out? Comes out as kinetic until it hits the ground. Once it hits the ground, how does it come out? Sound, and probably a little bit eventually of thermal. Correct. So let's talk about this guy. Okay. Essentially, pulling electrons through the air is the same thing as pulling that ball down. Energy has to come out in one of several ways. What are they? Light, sound, thermal. There you go. As a matter of fact, only difference between the ball dropping and this one is the production of light. In that particular case, which we could certainly get into potentially a little bit later on. Yeah, there it is. We can still get electricity through an insulator, you just gotta pull harder. Now, what essentially makes an element a good conductor? This is going to be a very quick conversation. There's a very in-depth conversation. It's probably meant a little bit more for my Chem 2 people and future Physics 2 people, but it's not meant. You don't have to like get super into the weeds on this. But I do want you to probably pay attention. What makes an element a good conductor and why? You guys have been in chemistry, so you definitely know that you got the left side of the table and the right side of the table that regularly form ions. Why? Because it has to do with the structure of the atom. In a nutshell, each row essentially is kind of how far the electrons are away from the center. Now, in a nutshell, chemistry works on this. Positives and negatives attract, and negatives and negatives repel. So here's the other gist that is super quantum, but don't worry about it. You guys remember this: orbitals. They go in a very particular orbital for some reason that, if you're really curious, come to chapter 28 of Physics 2 and we'll get there. All right, here it is. So you got, let's talk about this row right here: lithium, beryllium, boron, carbon, nitrogen, oxygen, and I'm going to go over here, fluorine. At fluorine, what you've got is that all of them are essentially in the same particular area. But as I go from boron towards fluorine, you got to understand that the nucleus keeps getting bigger. I add one more proton, one more proton, one more proton. Now, the electrons don't really get that much further away. So if I'm adding more positives, I'm pulling on each individual electron because they're spaced out. They're not all in one spot. So you can kind of think about the entire nucleus, all those positives pulling on one single electron up here. So as you go from boron, carbon, nitrogen, oxygen, and fluorine, as we keep adding one more proton, it pulls harder and pulls harder and pulls harder at the same distance. So now at fluorine, you've got one more spot right here for an electron in that orbital. And you have a stupid size of a nucleus. It's got right now 9 protons to hold on to one single electron. We're at a 9-to-1 ratio. That holds on incredibly, incredibly well. So what does it do? It usually finds something else that's not holding on to its electrons well, rips it away, and becomes negative. So you go, oh, that must be a conductor. Except no, it's not a conductor, because the moment it rips one electron away, it's got a full orbital. Is it going to keep pulling electrons away? No. So that makes it a great insulator, weirdly, despite the fact of its electronegativity. Now, if we jump across the line 9, 10, and step over here to sodium, you go, well, freaking sodium has a bigger nucleus than fluorine. Yes, except because it steps out to an orbital that is almost 2-3 times the distance, even though it has a bigger nucleus, that electron is now stupid far away compared to these that were in there ahead of time. So what happens to what happens to the force? If you got more charge, you get more force. What happens if they're further away? You get way less force. So is this last electron held on very well at all? No, it's not held on very well. So what happens? It usually gets kicked off, usually become a positive ion because it's missing electrons, see previous conversation, and comes back here, it's got a full shell, and weirdly, actually, sodium, losing its electron, holds on better to its nucleus than neon does, which is considered inert, because it has an even bigger nucleus than neon does. So basically, here's what you got, okay? Over here on the right side, you got the nucleus is too big. It grabs electrons, and then they don't move. And on the left side over here, you kind of got the opposite side of the Goldilocks situation. These nuclei are too weak to hold onto their electrons, so they lose an electron, and then they're good. So what do we need to make a good conductor? We need a nucleus that is just right. Essentially, here it is. Let's draw a picture here to give you annotations. All right, put this up. Okay, you need a nucleus that essentially, Fe is going to represent the nucleus. Okay. With again, let me write a visual here for people on it. With fluorine, 1, 2, 3, 4, 5, 6, 7. Terrible glue stock structure there, but we'll deal with it. Okay. Fluorine has such a large nucleus that it grabs electrons and becomes negative, but then it stops. And sodium is so weak to hold on to this guy because it's too far away that it usually loses that guy and then stops. But iron and metals in the middle have the just right nucleus, meaning they are strong enough that electrons don't just jump away, but they're also weak enough that the electrons are kind of allowed to move in between atoms on the outside. We call this situation the sea of electrons. Essentially, you got nuclei that are just there, kind of like roughly monitoring the electrons, holding them enough that they stay around, they're not going anywhere, but also they're not specifically staying in exactly one spot. So that argument once again, that statement once again, what makes a good insulator is simply this. Okay, this side right over here, too strong. This side right over here, too weak. And right here in the middle is just right. That's where you're going to get all of yours. And that's why metals are typically what you would ascribe to being a conductor. Now, most metals that you see are pretty much what metal? Predominantly. They're usually a mixture, an amalgamation. But what metal up here is most metals that you're looking at, like the stools. There's actually two major answers, I would say, but predominantly it's more one than the other. What's that? What'd you say? Oh, okay. What'd you say? Iron is the main one, yeah. Iron is the main one due to its prominence, its malleability. I'm saying iron right here, you'll notice it's just nice right in the middle right there, okay, is its predominant one. What's probably second most prominent? Copper's certainly up there. I would probably put it 3, but not in this room. Now look at that, aluminum. Aluminum, by the by, like I said, you might notice that, hey, Spainhour, that's starting to get over to the right side, and you are somewhat right about that. Like I said, all of these are usually alloys, meaning they're usually a rough mixture of all of them. All right, so let's get to the bulk of today. So a minute ago, I told you how to make things charged, right? Let's go back, discard this. We'll keep for a second. Right here. Okay, I gave you this very generic, how do we make things charged? Okay, negative, positive. How do we get negative? We need to get electrons. How do we become positive? We need to be missing electrons. I have given you one demo on this already, so I'll remind you of that demo. I think I was doing it briefly when we left the other day. Apologies for those of you online. Again, this is where the demos are really going to struggle. But we take a piece of tape, right? We put it face down. Now we take another piece of tape, and we put it on top of the other. Now, the key thing about these two pieces of tape here is that I'm not putting them sticky to sticky or smooth to smooth, but I am putting them sticky to smooth. So, I think I've commented on this a few times, so this should be easy. Which one holds on better? Sticky side. Sticky side. That's why it's sticky. Literally putting this sticky on my skin is sticky right now because the protons in the sticky thing are holding on to the electrons of mine extraordinarily well, such that if I were to pull it off, you could feel the pull, you could see the pull on my skin as those electrons are pulled. On the other hand, I put the sticky side down, of course, and practically nothing. Now, do I still feel a pull? If you put something smooth on your skin and pull it away, can you actually still feel a little bit of a pull, a feeling of that? Like put a pencil on your skin. So you got, most of you have pencils, put it on your skin, okay? And you can feel it on your skin, right? Now lift it away slowly. Do you still kind of feel a little bit of it coming up? Yeah, there should be a little bit, not much, obviously. Now, you put sticky to smooth, who should win that tug of war? Sticky. And so this is made of a stupid number of positives and negatives. So as it gets into this tug of war, and the sticky side wins, it of course becomes negative because it has excess electrons. And the other side becomes positive because it is missing those electrons. Which ones is it missing? The ones that this has in excess because conservation of charge. And now you get attraction between the two of them. Now, of course, I could do something else here. I don't know if I did this demo last time. This is maybe potentially a unique demo. Okay, I'm taking both pieces of tape for those of you online, and instead of putting them together, I'm putting them both on the exact same material. Okay, so both sticky sides are on this desk. And does this desk have positives and negatives? Yes, and if you had to guess, just running your hand along the desk, which probably holds on better to electrons, the sticky side or the smooth desk? Probably the sticky side. Right, which means if I pull off both of them, they should probably both be negative more than likely. And therefore, oh darn, this is kind of harder. You'll notice they repel each other in this particular case without actually touching. For those of you guys online, it is actually working. Okay, it's important for me to know that the demo is in fact working correctly. All right, so let's get into the first type of charging. Charging is going to essentially be on the macro scale, on spin hour, great, all this stuff, on the stuff that we can look at. How do we move charge around? Okay, the first type is charging by friction. You literally just saw it a second ago with the tape, but I got a bunch of demos that I'm going to use in here. Sorry again, people online. So here's the demos that I'm using. Let me describe them, not because you guys can't see, but again for people online. Okay, this is known as an electroscope. It looks very, very fancy, and it really, really isn't. Okay, you can make an electroscope out of much simpler devices. This one just works particularly well. Let me describe the electroscope. Those of you online, definitely look this up. Okay, an electroscope in a nutshell is this. It is a piece of metal, which of course is a conductor, letting electricity flow very easily. And if you'll notice, it is insulated everywhere around it. Most of around it is air, okay, on all sides of it. But right here where it might touch, right here in the middle, there is a very large plastic piece so that it cannot be gotten rid of, it can't be touched. Even if I touch this circle right here, that's actually not going to be conducting to this right here. So I have a piece of metal essentially hung in the middle of the air. It's basically what an electroscope does. Okay, now what does an electroscope do? An electroscope checks, gives us a visual indication on whether or not there's charge on an object. So here I have, for purposes of friction, okay, a fur, okay, and this is actually a rubber rod. It kind of looks metal and black. It's actually a hard rubber, which you might note that fur is an insulator and a hard rubber, also an insulator. But to be fair, the demo I just did with the tape, both of those are actually insulators, right? You wouldn't expect tape, either the sticky or the smooth side, to let electricity flow through it very easily. You wouldn't make wire on your electric motor out of pieces of tape. That's a terrible idea. So here's what I do, okay? And for the sake of the lab tomorrow, I'm going to describe what I'm doing very carefully so you can do it yourself. When you charge this by friction, okay, you want to get a firm grasp on it, okay? If you just do this, it's not going to do much. Firm grasp on it, okay? You can hear actually electricity happening, which I'll talk about in a second. Okay, a little bit, and voila. So what just happened? Well, for starters, if you had to guess, which holds on to electrons better? The fur or the hard rubber rod? What's that? The rod. Because fur, if you really zoom in crazy hard, doesn't have very much hold on to electrons on its outside. There's not much, it's all very thin. You get a very similar effect, by the by, with your hair and a plastic comb, right? Some of you, depending on your hair and your hairstyle and how it might get this regularly happening to you in the winter when you just take a plastic comb and comb your hair, and it sounds staticky. It's the exact same type of thing. What's happening? You're putting these in contact with each other. This one holds on better, so more than likely this is what charge? Negative, correct. So what did I do? We'll talk about that part in just a second. Okay, what I did is simply touch here. And what do negatives do to other negatives? Repel. So what did the negatives do? The negatives don't want to stay on here, do they? Why do they stay on here? There's nowhere else to go. Surrounded on all sides by it. By the way, if this was a metal rod, would this work? If this was a metal rod, I could probably put electrons on here, but where would they go? Into the conductor, for the people online, I'm pointing to me. into the conductor that's touching them, into me. So the electrons potentially in this area are in fact going into me. It's just that not all these kind of, when you look at this rod, don't think of it as like kind of flowing around here, because it's an insulator. Okay, watch this as a matter of fact. Okay, get rid of that, and again I'll talk about that in just a second. I touch it in one spot. Okay, I get rid of the charge. Watch this. This is not void of charge. It has it in other spots. So I'm kind of moving all the electrons around there. So now how does it work? Well, the negatives repel each other, and what do they do in a metal? They simply spread out. Because they can move wherever the heck they want. Now what do negatives do to other negatives? They repel. So what are they going to do in here? They're going to spread out. So what charge is this? Negative. What charge is this? Negative. And what do negatives do to other negatives? They... And thus you get this little hand in the middle moving, showing me that I have a charge. Now let's bring up to the second point up there, okay, the next type of charge. So, okay, now my apologies, I'm getting ahead of myself. You get this look if you've ever seen balloons, right? If you charge two balloons with your hair, okay, and put them next to each other, what are they going to do? They're going to repel. The balloons are being charged by friction. But we have another type of charging known as conduction. I will go back and forth between calling it conduction or its more colloquial name, contact. Charging by contact, it's all the same thing. So if you hear me say charging by conduction or charging by contact, I mean the same thing. And what does conduction do? Very, 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 very simple. Electrons spread out. So if I touch them to a piece of metal like this, they're simply going to spread out. It's like this. This is what I use to describe it. Imagine, if you will, I put all of you guys in this back room back here, okay? And imagine you bounced around like random. No concern for your pain or self-saving. You just bounced around at random, okay? Now, I got the door shut. I now open the door. What are we going to find? Even if at random, I walk away, I come back. Where are we going to find most people? Why? Simply put.
They go from low concentration, high concentration.
No, you get too complicated with it. Yes, you're not wrong, but don't lose the simplicity of it. Why are there more people out here when I come back? More space. Literally. Now, reverse the process. You're 100% right, Lillian, that it is high concentration, low concentration, because even if I had you bouncing around out here and this door was shut, and I opened this door, eventually would we expect people to be back here? Of course, a class of 6 people, this is a little bit hard to think. So imagine like 30 people are in class, all right? So 30 people are bouncing around in the room. Okay, I open the door, I come back. Do we expect some people in the back room? Yes, where are still more people? Why? More space, very good. Now, it's a little bit weird on whether or not humans are insulators or conductors. For the sake of today, we're kind of both, but I'm treating myself right now very much like a conductor because I am. If you had to guess, what charge am I? Neutral. Nothing's happened to me, absolutely. So I should be neutral. Now, as I'm standing right here, okay, being neutral, I serve as a empty room. So what happens when I touch this? I didn't take them per se. What did they do? They spread out. They spread out. Now, why does it appear there's almost none still on there? Why did they all go away? Well, if we looked at people in the back room versus people out here, would you see very many people back here at all? Almost like there's none at all back here, because why? Why is most of the charge out here? Because more room, more space. So why did it go into me? More space. Finally, this is what's known as grounding. Okay? Ultimately, grounding in a nutshell is on every outlet there's a third wire that is directly connected, guess where? To the, 100%. Yeah, grounding wires are connected to the ground. Okay, why the ground? Well, guess what charge the ground is? Neutral. So, and also I'm going to go ahead and say that on Earth, ground is the most possible freaking space that you can have. If I open up my analogy of the kids in the room and I open up the door to the outside, even if you're bouncing around at random, okay, and I leave for 5 minutes and I come back, where should I expect students to mostly be? And honestly, it wouldn't be unheard of to imagine no students are in the class whatsoever because there's simply out there more space. That's it. That's all it is. It's spreading out. Now, but Spainhour, when we put charge into the ground, doesn't it become not neutral? Technically, except if I take a hot cup of coffee, okay, and I go to a lake, and I just put the coffee into the lake, do you expect that, does the temperature of the lake change technically?
Yes.
Are we going to notice anything? So if I put charge out into the ground, does the charge technically change the ground? Technically, but it's neutral. So here's conduction in a nutshell. It's just simply spreading out. Now, you've called this, of course, and we'll talk more about this again in physics too, other things you've called this in the past is diffusion, going from high concentration to low concentration. But simply put, diffusion is basic physics, right? If I have, I'm pointing to the upper left for those of you guys online, all of my particles up here, I want you to imagine one particle, okay? One particle on the outside. Which way is this net force going to go? That way. So which way is it going to go? Out into empty space. Why? Because there's nothing pushing back. Now, what do you expect all particles to eventually do in what we call equilibrium? What would you expect, like with the 30 people in the room, what would you expect them to do in the room? If I open up the door and they're traveling around like crazy, how would you expect them to be distributed in the room? Pretty evenly spaced. Because when we talk about a lot of particles, evenly spaced out. Oops. Come on. I got stuff to do. Running out of time. I actually give these to your students. Oh, fair enough. Quiet as possible. You're fine. Okay, so when they're evenly spaced out, let's focus on this guy right here. Am I probably just as likely to get a force that way as that way? And am I just as likely to get a force that way as that way? And if you look at all of those forces, as I look at that, evenly spaced out is like saying I have an equal chance of getting forces on all sides, or the sum of my forces is 0. Equilibrium. So equilibrium is still Newton's first law. But when we look at a lot of objects, it's probably more like a likelihood of getting hit left or right or up or down. All right, I'm trying to finish here so we don't have to spend time on this tomorrow because I got 2 more to cover. And I'll go real quick here. Other ways of charging. All right. So we demonstrated, by the way, charging by conduction, by just simply touching, right? If a charge. Now, here's what's weird. The Wimhurst machine I showed you earlier is actually charging by induction. You go, wait a minute, it's not touching, it's jumping through the air. Yeah, here's what's happening. There's a huge insulator. Why is this happening? Because due to friction, this left side gets very positive and this right side gets very negative. And what do negatives do to other negatives? What do positives do to those negatives? So it's pulling them through the air to make that jump. And that electron, what you're looking at, that light, is electrons jumping from one atom to the next atom to the next atom, which is creating the light which you're looking at. This is weirdly charging by contact. You get the same thing anytime you get a static shock. If you reach out and touch something and you get a shock, it's probably because you've been charged by friction all day, more than likely between your clothing and your skin, and you've been doing this, or you've been touching other things, and you reach out and you're probably either very positive or very negative, let's say very negative, and the negatives in you are all repelling, and you get close to the door, and the door is neutral. What do those negatives want to do? They want to spread out, and they're pushing off of each other, and they jump into the door. That's that little shock that you see. That is technically charging by conduction or contact, even though it technically doesn't make contact. All right, let's knock out these last 2 because these are probably 2 of the more interesting ones. Charging by polarization. What charge is my electroscope right now? What's that? Why? Agreed. Why?
The electrons have spread out.
No. Equal number of
Photons.
But there are still on there, right? So watch this. Oh, by the way, I didn't tell you about this set. This is just the opposite set, okay? You're going to see me use this most often, the rubber rod and the fur, because because it's the best at it. Okay, the rubber rod holds on better, so it's negative. This is the exact opposite. Okay, so this is a glass rod or plastic, and silk or felt is usually what's used. Okay, so I'll do this, okay, and it's going to look the exact same. Why? Well, before I put electrons into it, what am I doing now? Taking electrons out of it, which makes it what charge? Well, it's not doing very well, but this one doesn't usually do as well. Should make it positive, correct. Now, to prove that it's positive, if I can pick up a charge for a second, there we go. To prove that it's positive, you can't really do that by visually looking at it until you compare it to something else you're pretty sure you know. For example, watch here, if I put another positive nearby, it pushes further away. If I put a negative nearby, it pulls in, tracks the other way. That's how you can tell whether or not something is positive or negative. Not in and of itself, but comparing it to something you already know. All right, so polarization, real quick. Whew, I gotta go fast here. First, I'm going to show you the cool demo. Okay? I don't know if you guys knew this or not about me. I'm a little bit of a wizard. Okay, this will be my wand. Okay, watch. Ooh. 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 Okay, not impressive, I get it. But here's what's happening. I am getting close to, but not touching the object. You know there's not conduction because you didn't hear that spark, that pop, that electricity jumping through the air, that electricity spreading out. So what's happening here? Why does it appear to be a charge even if there isn't? Well, for starters, to prove that there isn't, watch here. If I pull away, it's still neutral. So what's happening here is this. This is what charge? Negative, right? And they're not jumping through, so it's still staying negative, okay? But are there negatives up here, usually? And what do negatives do to other negatives? Repel. So what is it doing to these negatives? It's pushing them down here. So what charge is down here right now? Negative. And what charge is up here right now? Positive, because I just lost them. And if I take it away, what did the negatives on the bottom do? Spread back out, and so it goes back to being neutral. Polarization is the temporary redistribution of charge. You can pull this off with, like you see right here, you can pull this off with a conductor. You can also pull it off with an insulator like this. Notice I have a plastic plate, okay? This plastic plate right here, of course, is an insulator. My hair is an insulator, and this will work very similar to this demo I did just a second ago. I'm going to charge the plate. 2 seconds. Hold on, 2 seconds. Charging the plate. What charges the wall? So it should technically stick. But what does the negative in the plates do to the negatives in the wall? Pushes them away. And then what's closer now to the negatives in the plate? Positives. And what do positives and negatives do? They attract. So it redistributes the charges so the positives are nearby. Now, last thing I want to say, and then I'll move on. I got to finish induction real quick tomorrow. My apologies. I just want to do this so we can get to the lab as quickly as possible tomorrow. Okay. Will that plate stay up there forever?
No.
As a matter of fact, will anything in this room stay charged forever?
No.
Why? What is always happening to it that's keeping it from being charged forever? Air is running into it, knocking off electrons or giving electrons too, which is why I need to do all of my demos ideally when it's cold outside, because cold outside means less water in the air. Water in the air means it's way better at doing this, so nothing stays charged, which is why you get shocked in the winter much more so than you ever get shocked in the summer. I'm done. Thank you. We'll finish that first thing tomorrow. Hopefully that was okay, people online.